So here we're going to review completing tables, which we practiced right before Thanksgiving. So number 1, when you plugged in the -1, so that means -1 times -1 times -1, which will be -1, add the 1, means we have -1, 0. Then we've got 0 to plug in next for x, so 0 cubed plus 1. 0 cubed is 0. Add 1 to that. So that's our next value. And then 1 means we've got 1 cubed plus 1. 1 cubed is 1. Add 1 to it means my third value is 2. Going over to number 2, the equation's pretty similar, except for this negative right outside here, which is why I wanted you to practice this. This negative takes place after you cube the x. So whatever x is, you cube it, and then you add the negative to it. So our first one is y equals negative, and then -1 cubed plus 1. So we do this part first. -1 cubed is -1. But because I have this extra negative, a negative and a negative makes a positive. So 1 plus 1, which is 2. Putting a 0 in, a negative doesn't affect 0, so it's just 0 cubed plus 1. And that is, again, 1. And then we put in the positive 1. So we have y equals negative, and then 1 cubed plus 1. So again, we take care of this part first. So 1 cubed is 1. Bring down that negative, and -1 plus 1 is 0. So there are your two tables. Again, I wanted to make sure you had practice with that negative on the outside of x. We are starting 4-1 notes today. Exploring exponential models is what we're going to be working on today. So make sure you have your copy of the notes out, ready to go. The exponential function that we're going to be working with is y equals a times b to the x. Now keep in mind, only that b is connected to the exponent, and that's very important here. So b is what we're going to be referring to as a constant. And x will be here as our variable. Now the first thing we're going to work on is graphing an exponential function so you can see what it looks like. And again, exponential because it has an exponent in the problem. So the first thing we're going to do is what you were doing all last or before break, which is you're creating a table of values. After we've made that table of values, you're then going to plot the points. So our first example is we're going to graph the equation y equals 2 to the x. So x, the exponent, is what we're going to be plugging numbers in. Now, if I were to plug a negative in, then it would be y equals 2 to the -1. We haven't really touched upon negative exponents, but it is an Algebra 1 skill. And when you have a negative exponent, remember it means this number drops. So the 2 goes to the bottom of a fraction, 2 to the +1 now. And then on top, since there's nothing there, we put a 1. So this means y equals 1/2. If you need help on remembering your negative exponents, I would search on YouTube for simplifying negative exponents. Now you don't have to necessarily use negatives, but sometimes you'll see them in the tables. Okay, so after -1, I'm going to put in 0. So it's now y equals 2 to the 0, because remember x is the exponent. Well, another thing to remember, anything to the 0 power, hopefully you didn't just say 0 there, it is 1 every time. So this is the ordered pair 0, 1. Never 0, always 1. Next I'm going to put in 1. So it's going to be y equals 2 to the first. Well, 2 to the first is simply 2. And then we're going to put in 2 here. So it's going to be y equals 2 squared. 2 squared is 2 times 2, so that means 4. And we're going to go ahead and create one more row here. Squeeze this in here. I'm going to put in 3. So we're going to have y equals 2 to the third, 2 times 2 times 2, which is 8. So now we're going to take these points and we're going to graph them. So we start with -1 and 1/2. So left 1, then up half of a unit. Then we have 0, 1. One, 2, 2, 4, and then 3, 8. Now, you're noticing, hopefully, that there's a nice curve here. That's part of the exponential equation here. They'll always have a curve here, so we're going to connect those dots. Now, on the left-hand side, you're going to have the curve like that. It's not going to cross the x-axis because negative exponents don't make numbers negative, it makes them fractions. It's closer and closer to 0. So what we have here is what we call an asymptote, because the exponential function is never going to quite reach it. It's always just it's going to get closer and closer to it, but never actually reaches it. So here's our asymptote. And every exponential function has one. Now, when you have a horizontal line, that means that there's going to be a y equals, and the y value is 0, because that's what the line is crossing through. So here is the table and graph of y equals 2 to the x. And again, every exponential function will have an asymptote. Y equals 0 is the most common one. But it's not a guarantee that it'll be that one. Here is the problem that you're going to try here. You're going to graph y equals 3 to the x. You don't necessarily have to use a negative value for x if you don't want to. So go ahead, do this. Check with a neighbor either as you go through it or once you have your graph. And then unpause the video to check your work. So I'm going to put in numbers 0, 1, 2, and 3. If you'd put in a -1, I'm going to put that up here, and we'll go back to that at the very end here. So your values for the y column, for 0 you should have gotten 1, because again anything to the 0 power is 1. When you put in 1 it should have been 3. 2 was 9, and then when you put 3 in it was 27. Now hopefully you'll go, well my graph isn't that big, and that's okay. If you end up with a number that's too big, we're just not going to graph it. Now if you had done the -1, it would have been y equals 3 to the -1. which means that 3 has to go to the bottom, and the 1 becomes positive. Since there's nothing else in the problem, that means we put a 1 up here. So y equals 1/3. 1/3 is the decimal point 3 repeating. So you'd be estimating where it went on the graph if you were to graph that one. But let's go ahead and graph the other 3 points, because again, we can't graph this one right here. So we have 0, 1. 1, 3. 2, 9. So we can see how we would connect this part here. Now, here is one reason the negatives can help you, because if we graph that negative, we're at -1 and 0.3, which is right about there. That helps remind you that it's going to get closer and closer to 0, but never quite reach it. So hopefully, if you didn't, make sure you fill it in now. You also drew the asymptote. Again, we call this line y equals 0. And there's the graph of your second exponential function. We have a few vocab words here, one we've already talked about. Exponential growth means that as the value for x increases, the value for y also increases. Exponential decay means that as the value for x increases, the value for y decreases. So it's kind of like negative slope, and exponential growth would be positive slope. And an asymptote, we showed 2 of those lines here, the dotted line. It's a line that the graph approaches, so it gets closer and closer to it. But never touches. So those are your 3 vocab words for today. To identify exponential growth and decay, you're looking at the base. If the base is less than 1, then we have decay. And if the base is more than 1, we have growth. Now, we have to make sure you label the actual base correct. The base value is called the growth/decay factor. And it is the number attached to the exponent, because that's the base. So the number on the outside of it, this number right here, that does not have anything to do with whether it's a decay or growth. It's only the number attached to the actual exponent here. So I'm looking at 0.95 is my base, and that number tells me if it's decay or growth. Since 0.95 is less than 1, this is an exponential decay. So go ahead and try the next few tries, check with your partner or a neighbor, and then unpause this to see if you got them right. On the first U try, the number that you should have based it off of is this 2 here. Again, don't get fooled by the number that is being multiplied by. The base is only the number attached to the exponent. 2 is more than 1, which means this one is growth. The second U try, the number that you should have based it off of was 0.75, not the 11. 0.75 is less than 1, so we call this decay. Now to model exponential growth, we have two equations here. The first equation models growth, and when it models growth, it has a plus sign in the formula. When it models decay, then it has a minus sign in the formula. Besides that, they're exactly alike. A is your amount, the capital A is your final amount. Little a is your initial amount, so kind of what you invest or what you borrow. R is the rate, so that's your percent. And T is the number of time periods. Now, with the rate, one thing to pay attention to is you have to change the percent to a decimal. Our first step in order to solve these problems is we're going to identify or define the variables. And then we're going to substitute the values into the appropriate formula. So our first example says we've invested $1,000 in a savings account. It pays 5% annual interest. How much money will be in this account after 6 years? Well, is this a growth or a decay? Is your money going to increase or is your money going to decrease? And in a savings account, it should increase. So this is a growth, which means I'm saying A of t, which is the amount after how many time periods, equals lowercase a 1 plus r to the t. So we're using this formula. So our initial amount is 1,000. The percent is 5%, but we cannot leave it as 5%. So to change a percent to a decimal, we move the decimal point 2 places. So 0.05. And the time period is 6. So we plug it into our formula here. So A of t, which means A of 6, equals lowercase a, which is our initial or 1,000, times 1 plus our rate, 0.05, and then to the 6th power. So order of operations says we do our parentheses first. 1 plus 0.05 is 1.05. And it's being multiplied by 1,000 and raised to the 6th power. So think back to your order of operations. Exponents come before multiplying. So we're going to do this part first. In your calculators, you'll look for that arrow key. Looks like this for some of you, or you'll look for the button X to the Y. So whichever one you'll have, you'll type in 1.05 first, then either one of these keys, and then 6. And for some of you, it might not be X to the Y, maybe it's Y to the X. Same button. If you got 1.340, then you did it correctly. If you got that and a neighbor did not get that, if you would please take a moment, pause this if needed, and help them figure out how to correctly work their calculator. So now we take 1,000 times 1.340, and you should get 1,340. So in 6 years, he should have that much amount in his account, which is more than what he started with, and it's free money since it's interest. So it's a good amount to get $340 extra. Last problem of the day is a you try. So go ahead, read through this, do your best on it, then check with the neighbor if you need to. And then unpause this to check your answer and make sure you're correct. The first thing is to figure out if it's growth or decay. We're talking about a savings account, which means we'd be looking for more money in the account, so that's growth. We start identifying our variables. Our initial amount is 500. R starts off as 3.5%, but since it had a percent sign, even though it's a decimal, it still has to be moved. So we go 1, 2, which means our rate is 0.035, and our amount of time periods is 5. So A of 5, because we want to know how much is in the account after 5 years, equals 500 times 1 plus 0.035 raised to the 5th power. So we do our parentheses, and we have 1.035 to the 5th power. Remember, we need to do the exponent before multiplying. 1.035 to the 5th should give you 1.188. We multiply that by 500, and when we round it because we have money, we have approximately $593.84. So hopefully you got that answer, and again, remember it was rounded because money cuts off after the second decimal place, your hundredth.